Hey kids, Flexing Teacher Weber here. I hope you're having a good day. We have started a brand new unit on algebraic patterns. And I really feel like algebra is one of the most misunderstood parts of math. Algebra is really a way of using mathematics to explain the real world and to make applications in the real world. I talked to the kids about how scientists have discovered all kinds of different reasons why zebras have stripes and why some animals have different colors. And mathematicians were actually able to take all of that data and use math equations to predict, what color animals would be based on different criteria. So algebra really is the language of taking mathematics and explaining the real world with it. What we did in this activity is we started off with a couple of patterns and saw all the algebra in those patterns. So the first pattern we looked at, and we actually built this in class with pattern blocks, is we built banquet tables that have a special triangular attachment for kids to sit at with their parents. And we wanted to count the number of chairs you could get at each table. So in the first diagram, you could get 1, 2, 3, 4, 5 chairs. And then you could also get 2 at the end. So in diagram 1, you had 7 chairs. And then in diagram 2 right here, you could get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you could get 10 chairs, and then you could get the 2 on the end, right there. So in diagram 2, you could get 12 chairs. And then in the third diagram, you could get 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. You could get 15 chairs there, and then you'd get the 2 on the ends. So in diagram 3, there were 17 chairs. And then in the fourth diagram, you could get 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. You could get 20 chairs there, and then the 2 on the end. Right there and right there. So in diagram 4, there were 22 chairs. And I did those patterns in specific colors for a reason, right? We could always take the first diagram times by the 5 red chairs and add on the 2 side chairs. Diagram 2, take the tables, multiply by the 5 red chairs. So 2 tables times 5 is 10, plus the 2 ends. In the third diagram, 3 tables, 1, 2, 3, times the 5 chairs is 15, plus the 2 on the end. In the fourth diagram, take the tables, there are 4 of them, times the 5 red chairs is 20, plus the 2 on the end. And that's the algebra in this. Now what we did in this problem is we wanted to represent that algebra in many different ways. So the first way we did it was in a chart. And we have table 1, 2, 3, 4. And we know in table 1 there are 7 chairs, table 2 there are 12, table 3 there are 17, and table 4 there are 22. We also recognized here that the chairs pattern in this situation is increasing by 5 chairs every time. And look at that. So I want you to make a lot of connections here. Look at this. It's increasing by 5 every time. That's the 5 red chairs, right? That's the 5 red chairs every table. Okay? So 1 table times 5 red chairs. 2 tables times 5 red chairs is 10. 3 tables times 5 red chairs is 15. 4 tables times 5 red chairs is 20. That's the beginning of the algebra pattern. So the beginning of the algebra pattern is to take those tables, and multiply by 5. A lot of color changing here. It matters. So 1 times 5, 2 times 5, 3 times 5, 4 times 5. That's the beginning of the algebra pattern. Now, also, we have to worry about those n chairs, right? It's always 2 n chairs. Always 2 chairs added on at the end, the 2 blue ones. So that's the second part of the algebra pattern, adding on the 2 blue chairs. So plus 2. 1 times 5 plus 2 is 7. 2 times 5 plus 2 is 12. 3 times 5 plus 2 is 17. And 4 times 5 plus 2 is 22. That's the algebra. That's the algebraic relationship between the tables and the chairs. Tables times 5 plus 2. Now, what we did next is we represented these situations as an expression and an equation. Okay, so tables, we said x. We want to show tables times 5. The way we show tables times 5 is we write 5x. And then the plus 2. So 5x plus 2. Okay, this part, 5x, means 5 times the number of tables. 5 chairs at each table, or the 5 red chairs at each table. 5 times the number of tables. And plus 2 means the 2 end parts. The equation is the exact same thing, except we add on the variable y for chairs. So we write 5x plus 2 equals y. Or we could write this as 2 plus 5x equals y. Or we could write it as y equals 2 plus 5x. Or we could write it as y equals 5x plus 2. To get the number of chairs, y, you take 5 times the number of tables, 5 chairs at each table times the number of tables, and you add on the 2 n chairs. And that's the algebraic equation. Typically in algebra, we call the x the independent variable, because that's the one we change ourselves. In this case, we're always determining the number of tables, and the y would be the dependent variable, the dv. However, it can change, right? If we change the number of chairs, decide to do that, then the chairs would become the independent variable, and the x, the number of tables, would be the result of that. So it can change. So next thing we did is we made our algebraic equation and expression. After that, we used substitution. We used our equation to find the number of chairs that go with 100 tables. So we want to write down our equation. I prefer to write the one that starts with y. Y equals 5x plus 2. And in this case, we've been given 100 tables. So that's our given. That's our independent variable. We've been given that x is 100. That will determine what y is, so y will be our dependent variable. So we solve by substitution. Y equals 5 times 100. So we replace the x with 100 and use parentheses to show the multiplication. Then we use order of operations, do multiply first, 500 plus 2, and y equals 502 chairs. And that's how we use the algebraic equation to find any number of situations. So no matter how many tables we have, we can always determine the number of chairs. Last thing we did is we did some graphing. So we want to write 5 ordered pairs for this problem and graph the tables and chairs. So an ordered pair is an x and y value. And this represents a point on a graph. So our ordered pairs we can get from our table of values. So when X is 1, y is 7. X is 2, y is 12. X is 3, y is 17. X is 4, y is 22. So let's write these ordered pairs. So X is 1, y was 7. 1, 2 tables, 12 chairs. 3 tables, 17 chairs. And 4 tables, 22 chairs. Each of those represents a point on a graph. Still tables and chairs. Now let's make our graph. So this is the coordinate plane. We have an x-axis that goes horizontal. We have a y-axis that goes vertical. So we should title our graph. We could call it T and C, tables and chairs. Our x-axis will be called tables. Where the x and y-axis meet is the origin. So right here on my x-axis, I would call that 0. I want to make a nice large graph. So I'm going to skip every line. I'll go 2, 3, 4, 5, 6, 7. Now our y-axis is the chairs. And we want to have a good scale on this graph. It has to go up at a consistent rate. Now my chairs go 7, 12, 17, 22. I think I'll try going up by 3s. We have to go up at a consistent rate. So 3, 6, 9, 12, 15, 18, 21, 24. Okay. When x is 1, oh, look at this. I got to redo my x-axis here. There we go. So that should go 1, 2, 3, 4, 5, 6, 7. There we go. Now, when x is 1, y is 7. So that'll be like here. And I'll go right about there. And that's 1, 7. When x is 2, y is 12. So that's going to go right there. 2, 12. When x is 3, y will be 17. So that's going to go 3, 17, across and up. 17 will be right about there. And when x is 4, y is 22. So that'll put x right about the point right about there. And you can see you get a straight line. Now I wanted to talk about this straight line. We're not going to have any, typically we join the points, but we're not going to have any data in between those points. We're not going to have half tables or quarter tables. So all we're going to do is leave it like that. We're going to finish labeling our points, 317 and 422. And we always want to write the equation on our line. So this is the graph of y equals 5x plus 2. It's the graph of tables and chairs, which we call a linear relation. Okay, so look at all the ways we've represented this algebra. We've represented it as a graph, as numbers, as equation, as expression, all kinds of different ways. In my second video, we're going to look at another pattern where we can represent all the algebra. That's all for now. Flexing Teacher Weber, out.